We're going to talk about GraalVM native images. My name is Oleg Šelajev. I'm with the GraalVM team at Oracle Labs. You can find me on Twitter. I go by @Šelajev. I am just a few followers short of 5,000. So after this meetup, I expect to cross that. You can unfollow me in a week. No hard feelings. Yeah, no pressure. No, doesn't need to do that. Excellent. We just had a session about the GraalVM in general, the capabilities, what it can do, and figure out that it's a high-performance polyglot virtual machine for different languages, like JavaScript, Ruby, R, and so on. So, and this short presentation will be specifically about the native image capability. And as always, please do not make any forward-going business decisions based on the contents of this presentation. That is very important. Thank you. And let's go and talk about native images. GraalVM native image, available as an early adopter capability currently. What it allows you to do, it allows you to take your Java application and compile that ahead of time into the machine code that will not depend on the JVM. One of the main benefits of that is that it will run really, really fast. It will start really, really fast. So from not working, from not running a process, to being a fully functional, ready application to serve your users, it will be just a couple of milliseconds. And, well, let me just show you this. Right, so we're gonna go here and I'm gonna do this. So I'm going to use a quick start from the framework called Quarkus, and I hope it will start properly. So I will run this native application here, and I will start it, and it will start, and it starts in 74 milliseconds. That is fairly slow. Let me stop it. Let me start it again, and it starts in 24 milliseconds. That is better. It's a Java application, right? It's a small web service. A microservice, if you will, that starts in 24 milliseconds. And what I can do here now, I can just go to a random page and I can go localhost 8080, and I think it was prices HTML. So in my application there, that just started, it renders this HTML in response to an HTTP request. And it just randomly queries some data. And in the background, what it does, it has the Kafka, consumers, producers, and there are three components to this. One is generating random stock prices, like the random numbers, and sends them into Kafka. The other one takes them from Kafka, and the third one updates the HTML page or something like this, right? So it's an application written in Java that communicates with Kafka, that renders HTML, that accepts HTTP requests. And to start it, we didn't need to run this long process, and it starts in what? In 30 milliseconds. That is spectacular. Because normally you would not get the Java process to start this fast. Right? Because you will need to start the JVM. It will need to do all the things that JVM does. Right? It will need to initialize itself. It will need to load your classes, find the classes, verify the classes, start executing them using the interpreter for the class files, and then at some point of time it will just-in-time compile your class files into very efficient machine code, but that will be later, right? And so initially it will be a little bit slower to execute your code, and with the native images you get the instant startup. The startup of some milliseconds here, like 30 milliseconds. This is comparable to the startup of native applications written in Go or C or something like this, which is great, because if you now want fast startup, if you value the startup in your deployments, the startup time, then you don't need to migrate to those languages. You can continue writing your Java that you presumably, you might be more proficient in Java than in those other languages. If that's not the case, you can use whatever language you are proficient in, but normally Java developers are better with Java than, say, C++. Certainly in my experience. Still never remember which one is a dereference operator. Is it an ampersand or a question mark? It's not a question mark.
Not a question mark.
Maybe it's a hashtag. No. Right. So Oh, another cool bit is that let's examine this application ls minus la, right? So what we have is let's do human. So this file is 29 megabytes in size, right? 29 megabytes is larger than a couple of class files that are probably this microservice, but it doesn't have a dependency on the JVM. If I run otool, which is a tool to examine the file, you can see, oh my god, -l, where's, should show me, what happened, -l, maybe something else should be, print fact headers, load libraries, like, okay, -d, minus capital L, I think, I'll try, right, so it links to the couple of system libraries, and it doesn't depend on the JVM. So if you deploy applications, you can put it into a from scratch or a minimal Docker container without the dependency on the JVM. So you compare the size of this native application versus the size of the jar files plus the JVM. So, and in that comparison, 29 megabytes is a very good result. And also, let's run it one more time, because it's just like, why not? It just starts so fast, right? But what I wanted to show you is that if I look at this process in my activity monitor, you can see that it currently runs, right? So let me show you that there are no trickery. It runs, it renders my HTML, and it pulls some random numbers here. Come on, change. See, it changes, right? So it works. Now, if I look at this in my command line activity monitor, this process takes 14 megabytes of RAM. This is a Java microservice that starts in milliseconds and takes less than 15 megabytes of RAM. That means that you can run it in a fairly constrained environment. You don't need those beefy cloud machines to run your small services. You're still welcome to use beefy cloud machines for long-running processes where you need peak performance, but if you just need to spin something up, serve a couple of requests, write some data in the database, send a message to Kafka, you don't need like a large virtual machine for that. You can just use the smallest instances available, which is spectacular. So how does it work? Now, seeing is believing. Now you understand that this is possible. Let's talk about how it works. It works like this. So why GraalVM? Again, we're going to talk about this second line specifically during this presentation, right? So we looked a little bit about on the performance bits last half an hour, and looked a little bit on the polyglot and different languages during the last one. So now we talk about instant startup and low memory footprint. Mostly, where do you want those capabilities are the cloud deployments, right? Where you actually pay money for the memory consumed, which is usually it's even more expensive than the compute resource, the CPUs, and where you would like your services to be down most of the time, right? And then spin up only on request. Right? So in environments like function as a service, or where you have the fleet of microservices that you want to auto-scale, and you have like traffic coming and going, so you're not keeping the machines up and running all the time, but you want to be able to react to the traffic conditions like very fast. So this is where the GraalVM native images would be the best probably. Also maybe some user-facing command line tools, because starting an application like a command line thing and waiting a couple of seconds for it to react is maybe not the best user experience. You probably won't save much money by building faster command line tools, but you certainly will get the perceived performance experience. So how does it work? We're going to talk about standalone bit here now, and everything in this presentation is just for this bit. So if I will tell you that there are certain limitations to what it can do, I want you to understand that it is regarding this bit, and certainly not running in context of the JVM. Right? So that's important. So GraalVM native images. What it is, it's a fully ahead of time compilation of your code to machine code. GraalVM supports different languages, right? Java, Scala, other JVM languages, Kotlin. Yay. I see you. And so on. Also JavaScript, Ruby, R, Python, and so on. So we can compile ahead of time the Java bytecode, right? So we will not compile ahead of time the JavaScript bits of your application. So this native images mode specifically concentrates on the Java, but it compiles it to machine code fully. It still works with memory management, right? So you expect your program to operate under the assumption that memory is infinite, right? You allocate objects like there is no tomorrow. You're using memory. You're not managing memory manually when you write your Java application. So when it's compiled ahead of time to the machine code, like it should run the same way. It should run with the garbage collection and some memory management, because otherwise you would have to change your program, which is not what we want, right? So there is an implementation of the garbage collection that runs within the native image. This is not GC from the Java world. It's not the like G1 GC or Shenandoah or ZGC or anything like that. It's a different implementation that is currently a little bit simpler. I have more information about that, but there is GC and the other primitives and the components of virtual machine that are powering. So there are some primitives to handle thread shadowing if your program uses threads, right? And there are things to handle files and so on. So it works within the context of with some components of a virtual machine available. It still has secure execution. So like if you have a race, it's not gonna run like random information outside of the race, because like it takes the Java code and translates that to the machine code, so it executes within the boundaries. So if in the Java code there were like range checks and type checks and so on, those will be translated as well. And the result is embeddable in native applications, right? So imagine if you previously we had the native implementation of the JVM hotspot, and it dynamically executed class files which it found in jar files on the class path. So it loaded those bytecodes and then executed them. So when you produce a native image, then it compiles to one gray blob, the binary file here, right? So fully machine code. There is no dynamic execution of Java bytecode happening here on the right. Demo time. Let me show you.
What's SVM?
That's a good question. That's a good question. SVM is a code name, which should not be on this slide. SVM stands for Substrate VM, which is the name for the project within the GraalVM that contains the implementation for those components of a virtual machine that will be used within the native image.
Thank you.
Let me show you a demo. Right, so we're gonna stop this Kafka thing, and we're gonna show to this like next thing. I have a Java application here. Nope, it's a Java application here. What it does, it just takes the arguments and just it walks some file system paths and just updates some data. It's not exactly relevant what it does, it's just like some Java code, right, that operates on the local file system. What I can do now is I can build it. I will feed my Java classes, or I can feed my jar files to the native image utility inside the GraalVM home. So I'm going to run this, and it's going to run for a couple of seconds because it needs to do certain things, and I'm going to talk while it does so. I think I have 20 to 30 seconds for this small file on this particular MacBook. So what is happening here is that it analyzes the Java file, the bytecode, right? And it figures out which parts of the standard library and dependencies we are actually using, which methods called other methods. So it builds the full universe of the bytecodes that ever will be executed, and then it compiles them ahead of time to machine code, and it writes it out into a file. the native image utility is not by default in the GraalVM distribution. So when you download the zip archive, there will be no native image utility there. It's available as an early adopter special kind of plugin-like thing, right? So you need to use the GU utility, stands for GraalVM Updater, and you do GU install native image. So here I will show you. So in my GraalVM thingy, right? When I do bin, there is the GU. Where's my GU? There is my GU utility, right? So I will do GU install native image, and it will download the jar files and put it into correct places. And then after that, the native image command will be available. The same mechanism works for support for languages that are not in the main distribution. So you do Ruby, R, Python, right? And you get those languages inside the thing, inside your GraalVM distribution, because by default they're not there, right? But the file compiles, right? And if I do ls minus, what was that? LHH, list dir. It's a small file, 7 megs, kind of for hello world, not bad. And if I time this list dir working, so let me show you. I can do Java list dir running my Java class, and I will give it like whatever paths up to directories, and I can do the same with the time command. Come on. And you can see that it takes almost half a second on my machine, right? Because it needs to spin up Java and start executing some stuff, and then go through the actual file system and gather the file sizes or some metrics, whatever the Java program was doing. So now I can time the execution of the list directory with the same thing, and you can see that is almost immediate, and you can see that the outputs are the same, right? So it worked the same file system, gathered the same metrics, because it's the same Java program, just compiled ahead of time. But it started really, really fast, and it's just 7 megabytes, which is very, very good, which allows you to do small microservices in 14, or maybe like 30. So what happened during this? So this stage is very important, right? We fed our class files to the native image utility, and it did a lot of work, right? It took like almost a minute on my machine to do something. Obviously, we are making this process faster as well, so it's, but it did a lot of work. It looked at the programs, it looked at the class files, and like this is one application, one class file, but there is the full runtime library that this application can use. For example, from this application, you can get to the number format exception class, because your application can work the datetime formatting. Simple datetime format is the class that ends up in this native image. You know how? From this code. This is a good question actually. If you interview your junior Java developers, this is a good question. How this code can reach to the simple date format? Anyone knows the answer? Your application can throw an exception at any point of time. For example, Stack Overflow or whatever exception. And when you throw an exception, it gets propagated to the top level. There is an exception handler that will print it to the standard error output stream. And when you print the exception, it also can print some things. So there could be timestamps, and they could be serialized to string using the simple date simple date format. That's how this application actually reaches into the simple date format, which is non-trivial. But like to figure that out, like the native image utility analysis thing spends some time, right?
What about things like reflection and class path scanning, or?
That's a very good question. You know, like I will answer it to that in a bit. When I was in the university, I had this really bright professor, and they told me how to listen to lectures, right? How to listen to the people presenting you some information. You want to always keep up with what is said, right? And you want to be able to ask questions. So the good question, the normal question is, which has the answer on the current slide, right? If what you're currently looking at has the answer to a question, this is a normal question. A good question has the answer on the next slide. A very good question has the answer like several slides in forward, right? That means that you are within the context of what is being said enough to predict where will be the questions, right? What's interesting bits about what's currently happening, to predict that that information will be further, like several slides further. And then there is an excellent question, answer to which is on the next lecture. So, about the reflection and configuration, stuff like that, that is a very good question. We'll cover that today. You will not have to wait until my next visit to San Diego, but just in a bit. Right? So what is happening during the static analysis? Right? We take your application, we take the classes from the JDK, and we take the classes from the Tartu VM project, which is the components for the GC and the thread shuttling and other things that the VM provides. They're all written in Java, which is very good because we can compile Java ahead of time to machine code. And when we gather all those, we run static analysis, and we find the reachable methods fields, whichever bytecodes are calling to whichever things, and then we compile that because we have the compiler, right? We have the GraalVM compiler, which can be used as a just-in-time compiler, which means that it takes bytecode and the profile, and compiles that and outputs the machine code. But also, if you just give null, signature-wise, it takes the bytecode and the profile, which is non-existent, and then you get the ahead-of-time compiler. Practically speaking, it's a little bit more complicated because the optimizations are different for the AOT versus just-in-time, because it can speculate differently. But technically, you can imagine how one part is null, and then it works functionally. Right, so we write the machine code, we write some pre-initialized data structures, and we just wrap it into the binary for the operating system to be executable. And then we write it down into a file, and as you know, it runs without the dependency on the JVM. So there are clearly now two different stages for this. One is the build time for the native image, when we run the analysis, when we build this executable. And then actually the runtime, when we actually execute our application. So those two phases could be at a different stage and in different environments and in different points of time, right? That is something that you probably want to run in your CI environment. When you prepare the deployment, you want to run the build step. And this is what is actual runtime in production. So now, it's very important to have that separation in mind, because normally if you run Java my jar minus jar my jar, then both those things happen at the same time in a single environment, right? You initialize things, you read the classes, you figure out which classes call other classes, and that happens in production. So because of that, there are a couple of important differences between the GraalVM native images and running the normal Java application. For example, when we look at the classes, there are the static initializers. There are blocks that are used to initialize the classes when we just before they become accessible to the system, right? So by default, for certain classes, we can run those at the image generation time. We can also run them at the actual runtime, but for speeding up the startup, it's very useful to be able to run those at the image generation time. Which means that sometimes, and before it was done by default during the construction of native images, I think currently it's a mixed approach. For some classes, it's by default still. For some packages, it's done during the native image construction. For others, it's delayed to runtime. But the thing is that it was a conscious trade-off for the static initializers to allow faster startup by executing some code ahead of time in the generation phase. What it also allows us to do is to pre-initialize some data structures and write out the objects, the actual objects that will be initialized in the to the final image, right, to this runtime bit. For example, we don't need to initialize all the locales or date formats that ever could be accessible, right? We can just initialize a certain set. Or if your application pre-computes like the first million of prime numbers, we can do that at the generation time. And that data will be written out and then available for usage from the get-go when you start your application. So we can do that, but it also means that no instance-specific initialization can be done there, right? You don't want probably to start a thread or read a file in a static initializer, because that will be run in your CI environment. That would be like if you run your production configuration, that would be nonsense to run that in CI. Like if you read a property file, that's not what you want. So, or opening sockets or files. Like what should the program do with a file opened during the native image generation phase? It's not even the final runtime environment. So there are some limitations to what should be done. And as developers, you are in the full control of what your application actually does, so you can change those things. However, that can be inconvenient sometimes. So, for example, if you have a class like this, right? So what we do, we have the main method just prints two dates. One is the cached in the class called startup in the static final field here, and the other one is the new date, right? So when we run this on the JVM, then we'll probably get two startups, two timestamps, which are very similar to each other, right? Because we initialize this thing once, we print out two dates, maybe like a second will pass if you were right in the middle of the seconds. If you run this with a native image, so those timestamps are the same. With the native image, those would be different because the cached one, right, this one, will be pre-initialized during the startup, the image generation time, because it's cached in the static final field, which means the static initializer for the startup class, so which means that it could be allocated, computed, and cached and put into the final native image as a constant. So there could be differences in behavior. There are some configurations that you can use to figure out which classes should belong to which group. So you can make certain classes initialize at build time. You can make certain classes initialize at runtime. For example, if you seed your random number generator with some randomness, you probably want to initialize that at runtime. Otherwise, your random number generator will constantly get the same seed and will be random, but always output like 4, which is not very good random. So there are controls, there are knobs for configuring this thing. There are also many other knobs available. For example, reflection. Good question. Reflection is when we dynamically access some classes or data or call into the methods. You can configure reflection for that. The static analyzer cannot understand reflection fully in the general use case by itself because it's static, right? And for reflection, you can construct arguments dynamically. And you can say, oh, please give me this class string A plus string B at runtime, where string A comes from arguments and string B comes from network requests, right? And then you get the class and you call a certain method on that. So statically, you cannot figure that out. So you need help for the native image generation. So if you have a reflection target like this, so with a method greet, you can see my IDE didn't even highlight this as a properly used method for the screenshot, right? And you use it as, let's load the class for name, and let's say like this is our name class, and let's get the method from that, the constructor, and then execute that, and then get the method by name greet, and invoke that. So we construct the same program that we will normally do, right? But we do that dynamically at runtime. So the static analyzer cannot see through this. Maybe it could in this particular example because all the names are constants here, right? But in general, you can see that it could be made impossible to statically analyze this properly. So what do? You need to provide configuration. As a developer, you can turn the knobs in a certain way to say that, oh, here's a JSON file that says, please, on that class, please open for reflection the constructor and the greet method. Because as a developer, you know that you're going to touch those methods and execute those dynamically. Static analyzer cannot know this. So you provide some help by configuring this. And after that, those classes and those methods will be included in the final native image, and they will be accessible. So reflection works, but requires configuration. What else? Proxies. Proxies often are generated at runtime, right? The proxies to interfaces. Requires configuration. Calling to native libraries, GNI. Who uses GNI? Who uses libraries which use GNI? Who uses libraries which use GNI but they don't know about that? Excellent. You know, people who said they use Spring, you are using GNI in certain bits, almost definitely. Right? GNI requires some configuration for that. Something else requires configuration for that. Resources. When you say, oh, this is my cat picture that I want to serve as an icon for my site. You do that with class loader get resource my file, just please send those bytes to the browser. But the static analyzer cannot figure it out. It doesn't know that the files should be included, right? Because there is no dot notation that it can follow. So you have to specify that please include those resources. You can do that yourself, or you can use a certain framework that will help and like use convention or configuration saying that, oh, all resources from a certain folder should be included. But it requires help for the static analyzer, right? And then there are even more knobs that you can turn into certain configuration to help generate native images out of the programs. And all in all, the best bit is there are even more configuration. What you can do, you can provide a sort of overlay between how the native image generation will see the programs and how they actually are. So you can say that in a certain class, please substitute the method for this particular code, right? Or it can say like, oh, in that class, please do not look at this field, because you know that that field will provide challenges to the native image generation. So you have the full control of how the native image generation goes, which is great because as developers, you can solve problems. This is our most prized quality, to be able to solve problems that other software poses to us. Right, so you can do that, and if you want even more configuration, you can even determine in which phase of the runtime you are currently happening. Are you in the JVM, running on the JVM, or are you during the image build time, or are you in the image runtime? So if you're actually writing your source code, you can change even like specific things. So as a developer, you have the full control of how the generation happens. Also, as a developer, you don't have time to deal with those pesky details. You have deadlines and Jira issues, and you don't want to do that specifically. So you want some help. One form of the help is that all that configuration can be embedded in the artifacts. If you have a library, if you have a jar file for, say, netting, which probably powers quite a large chunk of the Java web applications, you can put certain files in the artifact at certain paths, right? And you can embed that configuration for the native image inside the library. So for example, if you know that native uses certain GNI or native uses certain classes and you need to open them for reflection, you can put the certain files inside your native archive and make it easier to consume and use in the native image, GraalVM native image thing. And native actually does that. Go native. So you can also provide more configuration and say that, oh, please use the certain resources or delay certain initialization to runtimes and stuff like that. So as a library author, you have the control how your library will be consumed within the GraalVM native image context, which is great. And then if the libraries are failing you, then you have to do the work yourself. Right, so native works, and there are non-trivial applications that actually work as native images. You can read a great blog post by Codrod on the team about how to compile native. He goes through the substitution mechanism and the configuration for reflection and so on, and also how we handle unsafe, because Java developers like the unsafe things where you use unsafe to write stuff in memory directly, right? You say like, oh, write by that offset in that object, and you're hoping that you get into the field, right? So that you write data into the memory box where the field should be. So when you run with the different memory layout compiled ahead of time, and you say, oh, please write by offset like whatever hex number, most probably you will just get into somewhere else's memory. In the best case, you will just crash. In the worst case, you will get a security vulnerability because you're writing into random memory locations. Most probably you will crash because it's unlikely. So there was a thing how to deal with unsafe as well. How many of you use unsafe? How many of you use libraries which use unsafe? This should be all of you. How many of you don't know that you use libraries that use unsafe? I have good and bad news for you. You almost universally use unsafe, which is probably mostly mediocre news. A question?
Yeah, so the things you went through where you have to provide configuration, how much of those are compile time errors versus runtime errors? Like, does the compiler, ahead of time compiler, look at your use of the reflection APIs and say, match it up to some configuration and say, okay, good, and if not, error? Or does it just, does it, and if it won't run at runtime if you don't provide that configuration?
Yeah, so those are the compile time errors, mostly, right? There is also this particular interesting flag that you can say, like, oh, please report unsupported things only at runtime. And then, of course, those things are reported at runtime. But then, like, you were the one to blame because you played with the wrong knobs in the configuration. But mostly, it tries to be like reasonable. It also gives you error messages which are different level of being cryptic. Sometimes they are more obvious, and sometimes they're non-obvious, and we're working on providing better user experience for that. So, like, to compile an application that doesn't compile currently, it's a challenge. It's an interesting task. It's an obstacle. It's a problem to solve. It's not impossible, but like it will require some puzzling and like tweaking things and figuring out. It will require some hacking in the original definition of hacking as being like figuring out things, right? So if you have like a large application, like WebLogic based something, most probably it will not work out of the box, right? Most probably you won't even be able to configure it to run as a native image. But if you start a new project, a new microservice, and you know that you want to run it with fast startup, low memory overhead, then you can use certain frameworks and applications, certain ways to ensure that from the get-go you are compatible with and you are within the boundaries of what's configurable or what's easy to configure. Right. Native works. Native starts really fast and takes less than 10 megs. I think this is the Hello World sample. Also, there are other frameworks which are supporting GraalVM native images. There is Helido by Oracle people. There is Micronaut by, I think, Object Computing, OCI. Object Computing, something, don't remember. There was also Quarkus by Red Hat. And Quarkus demo is what I showed you before. In general, they are starting up from whatever in hotspot a couple of seconds or like around the second, and then in the GraalVM native image mode that gets to the milliseconds. Right? There are differences in what the actual like numbers are, but well, if you look at the difference there, difference here is maybe not as important as difference with this, right? So the startup time is approximately 50 times faster. It could be debatable. The larger the application is, probably it can start a bit faster relatively, but you need to compile that. The memory footprint is kind of the same story, so it kind of works like this. Spring, for people who are using Spring, currently doesn't work as a GraalVM native image. There are some specifically crafted applications, Spring applications that work as GraalVM native images, but they are really specifically crafted, or less specifically, like maybe one specifically crafted. But out of the box, if you have a Spring Boot application, that will not work as a GraalVM native image. The good thing is that the Pivotal people the engineering team works with the GraalVM team, and both of us want to make that happen. So the Spring applications would be available to run as native images. And there is a wiki pages, and there are some timelines, and people are committing effort to make that happen. I think Pivotal announced that at Spring I/O in Barcelona this May, and I think the timeline for that was that they want by Spring 5.3, which is next year in Spring, to have that support in there. Of course, there is the question of other libraries, right? Because if you have your application and you want to use some random library from the Java ecosystem, it might do something that requires configuration. So you need to configure that. So Project Quarkus by Red Hat, they looked at the certain libraries which are popular and figured out how to run them and provided configuration. So Quarkus put a lot of effort into making this more accessible, the GraalVM native images. So the work in progress includes the Windows bits. We have the Windows experimental build of GraalVM available with the native images inside, so you can build some applications on Windows. I think that requires a specific version of Windows and some SDK in there for that to work, but you can experiment with that certainly. And also, currently we work on the Java 8 level because we have Java 8 based binaries. We're working on Java 11 based things. The future will show how much and how that looks like, because there are some functionality that maybe is more dynamic and requires some additional configuration stuff, like method handles, for example, where you can dynamically execute like random chains of methods, which is not as easy to AOT compile efficiently or in general. So that is work in progress. Do we have some time? Do we have time?
Yes. You guys have time?
Yes.
Excellent. We're gonna spend like at maximum like 10 minutes, maybe more. But let's talk about runtime. I'll be quick. Let's go hard and fast, just like we want our programs to run. So if we talk about the runtime characteristics, one thing is what is very important is obviously GC, right? If you imagine your GC in the native images, it's not your garbage collection implementation from Hotspot, but it's a customly written GC, and it's a generational scavenger, so it works approximately like this. If you imagine your Java memory management model happening approximately according to this picture, with some generation where objects are created in Eden and then promoted to survivor, and there are some young generation GCs, and there are old generation where objects surviving a couple of cycles are promoted, then the native image generation, native image GC at runtime looks approximately like this. So it's really good for throughput. It doesn't interfere with your running application very much, but it's not a low latency GC. So when the garbage collection actually will have to happen, it will stop the world, and there is going to be a pause in the execution. So the good thing is that your application starts really fast, so you can just kill the old process and start the new one if you want. But if you run your process for a longer period of time, right, then you consume the memory and you start like doing the GC, then you have to be prepared that there might be some pauses. Right? You can also tune that so you can say how much memory you want to give it, and I've seen examples of I think a Quarkus application. Somebody, Sunny Greenaver, from one of the founders of the Quarkus framework from Red Hat, he showed at Devox UK that the sample microservice can run with 1 megabyte of RAM. It ran very slowly, but it ran. With 5 megabytes of RAM, it ran decently fast as well. So you can tweak it, and you can give memory, and you can also print GC and see what's happening, so you have some visibility into this. Also, in the GraalVM Enterprise version, you can get the debug symbols and VM inspection, so you can actually take heap dumps and analyze that in the VirtualJUG, which is what, if you want that, you can have that. So that is supported, so you can see what's actually happening with the memory, if you want to tune that. But the actual production environment, you're most probably looking at the latency for serving requests and the throughput, right? So I run this net8 Hello World sample on my machine, as we know, not the most rigorous benchmarking environment, and I run that for say 30 seconds with 2 threads having 100 connections with the request rate of 2,000 requests, 2,000 requests per second, asking for that. And I have now 2 slides here, right? And one of them is the slide for the JVM running as a Java process, and the other one is running for the native image. And you can see that the average latency, however terrible metric that is, don't measure average latency. Like, doesn't tell you much. But the average latency is negligibly similar, right? So 1.4, 1.3 milliseconds. Mind you, it's just returning a stream back to localhost network, so it's not very impressive. But the requests per second parameters are also similar, 1993, 1962, right? So we run for 30 seconds, and if you run your Java application longer, the just-in-time compiler will kick in, will optimize code, and will probably have the better performance. But for initial X seconds, they're very similar in performance and latencies and whatnot. So for the first request, probably it will be even faster. I'm sure there is no time. This is just sorted by the latency percentile, right? But just with the native image, one request will be certainly faster because you don't need to initialize the JVM. You just will start up faster, serve a request, and die. And if you want to scale that in the same amount of memory as your Java process takes, you can fit like many. Like if you run your Java process and it takes like 300 megabytes of RAM, then you can fit there like 20 services that take like 15 megabytes of RAM. So the general throughput per unit of memory could be higher, but requires scaling. So it's interesting for certain environments, and maybe less interesting for others. If you want to run your IDE, for example, and you start it once in a month, then your startup costs do not matter much, right? If you run and start your things more than you actually process, because your processing is just accept request, take data from the database, send Kafka message, and send the JSON file back through like HTTP, then probably you don't want to spend initializing your infrastructure. You don't want to spend time more than actually processing, right? There is also the profile guided optimization bit as a performance feature. That is a feature of the GraalVM Enterprise Edition, right? Which is where you gather the profile, you create an image. It's a special instrumented image. You apply load, you gather the profile, and then you create a native image using that profile. So you get the profile, actually, so you know which code paths are taken, you know which data flows through, but you still compile ahead of time. So it's kind of like a halfway between the just-in-time compilation and ahead-of-time compilation. It's a ahead-of-time compilation with profile. So you cannot speculate too much because you cannot de-optimize and optimize again, but you can make sure that you use profile. And then the native image with the profile guided optimization is very close to the performance of the JVM. I think it's on par with OpenJDK performance. Of course, GraalVM Enterprise Edition gives you better performance on the JVM, but that's the other story, right? So if you want performance, like there are options for performance to opt in. But in any case, it will take milliseconds to start up, milliseconds to start up and lower memory overhead and runtime. So all in all, GraalVM, an excellent project, very interesting, can do many things, both for normal Java applications and compiled ahead of time Java applications, and other applications, and Node applications, and Python applications, Ruby applications, and R applications, and native applications, and other applications, all kinds of applications. So it's software platform for running software, right? The grand vision is that in a number of years, you want to run stuff on your computer, you will use GraalVM. We'll get there one language at a time. Excellent. On this very happy note, thank you very much for coming. This is it.
Thank you very much. So, did you want to take, is there any questions out there? Oh, we've got one. Okay, go ahead.
So you said earlier that Graal's on the JVM, it's using the JVM CI to inject a new, its own hotspot compiler, and then that was added in Java 9, but that Graal runs in JDK 8. So how's that all?
That's an excellent question. How is it that JVM CI added in Java 9, but we have binaries for Java in Java 8? We backported JVM CI to Java 8. That's as simple as that. So it's available because my experience for certain is that people are still running Java 8. I got questions today about running stuff on Java 6 just here earlier. So Java 8 seems like a good runtime currently, right? We would like to have the builds for Java 11, and so for example the compiler, just-in-time compiler works there, and the languages work there. The native image bit is not working. We are doing the development. You can follow that on GitHub, so you can see actually how it gets better and better. Windows support as well. So it's an open source software developed on GitHub. You can join, you can submit. If you try it and you figure out issues, or you were like, oh, this is the showstopper for me, or this is just inconvenient, or I just want this particular code to run faster. Submit GitHub issues. I think for the last year we closed something like 560 issues, maybe since like last May or something, which is considerable amount. I'm not sure, but yeah, stars on GitHub. I think we are close to 10,000 stars. Would be cool to be the most starred open source project at Oracle. Would be interesting. Yeah, so yeah, there is a significant amount of engineering effort involved in the GraalVM development. I think the team at Oracle is approximately 70 people, which is, well, not the largest team in the world if you look at the general amount of people, but it's not negligible, right? Excellent. Any more questions?
How does the licensing compare to the normal GVM licensing?
Right. How does the license compare to the normal JVM license? So the GraalVM Enterprise Edition is the proprietary product. So it has the special license, which you have to read, and I cannot interpret because I'm not a lawyer. And the open source bits are under open source licenses. We are trying really hard to be easy to understand. So the components are under the same licenses which are the original counterparts. So the Java related bits are under GPL2 plus the ClassPass exception, just like OpenJDK. The node bits are under normal license, which normal node is. Ruby bits are with normal licenses that Ruby has. I think R is GPL3, not sure, don't remember exactly, but our R is also GPL3, the same, right? So we want to be compatible with the existing things, right? So if you run OpenJDK, you can run GraalVM Community Edition there, right? The stuff. So our language implementations, the interpreters, which are not, which is purely our code, right? They're most often under the universal permissive license. You have to check the exact projects and their licenses. But the universal permissive license, which is a MIT-like permissive license for that code. And say Truffle API, the Truffle language implementation framework, I think also under UPL, the universal permissive license. So we are trying really hard to be like a good open source project, and we see some collaboration from other companies. Red Hat contributes fixes and some support for RH62 architecture, and some patches we got from Intel for like the compiler things, and so on, right? And the development goes forward. So licenses wise, check it with your lawyer, but we should be usable.
Okay, cool. Thank you again.